Hi, my name is Orso Meneghini, and today I'm going to talk to you about OMAS, a Python library to interface with the ITER Integrated Modeling and Analysis Suite. This is the outline of my talk. I'm going to first introduce IMAS, which is this universal language for fusion integrated modeling. Then I'm going to talk about OMAS and how it helps us work with IMAS. And finally, we're going to see OMAS in action inside of the OMFIT framework. So IMAS is the ITER standard for handling its data. This is used for both experimental and simulated data, and all of the ITER data will only be available through IMAS. IMAS is composed fundamentally of two components. One is the data schema, which defines the logical organization of the data, which it's right now organized in 67 containers, which are called the IDSs for interface data structures, which contains the different physics of a tokamak. For example, the equilibrium, core profiles, neutral beams, and magnetics, and so on. Each of these data structures are organized in a hierarchical tree, as I'm showing here on the right for the equilibrium and some of the physics elements that we're always familiar with. The second element of IMAS is its actual implementation, the software infrastructure. IMAS provides APIs for several languages like C, Fortran, Java, MATLAB, Simulink, and Python. And it stores data in different ways. These are called backends. You can store data to MDS+, HDF5, UDA, and so on and so forth. In short, IMAS can be thought as Fusion's best and more comprehensive attempt to build a standard data format. In integrated modeling, this is very important because the whole enterprise would be greatly facilitated by widespread adoption of a single standardized data format. So until now, people have been used this kind of a free-for-all approach where each code just uses its own format for inputs and outputs. This is great, but because it doesn't require agreement with other people. But when we are trying to put things together, the integration effort scales with the number of components that we want to integrate squared. Or the other approach is that when you're trying to integrate things, you only integrate things depending on the workflow that you want to execute. But then the issue with that is that your data flow and your workflow are really tied to one another, and that's really not ideal. If instead we use a standardized data format like shown here on the right, the difficulty here is that it requires coordination among all parties. Everybody has to agree to use the same data format. But once we have all components that speak the same language, then you can support this kind of a plug-and-play approach of components. And the neat thing is that in this case, the data flow and the workflow are really decoupled to one another. So the adoption of IMAS can occur at different levels. At the most tightly approach would see that the physics routine and the IO routines, they're all designed to use the IMAS data structure. The second approach is if you have, for example, some legacy code, you can redesign the IO routines to speak the IMAS language, and then you do some kind of mapping inside of the code itself. The third approach is that you leave your codes intact. They keep reading and writing the same files as they've always done, and then you do the mapping outside of these codes in some third party or code or routines. So what's inside actually this Hall of Rising Sun? Let's see what's inside of IMAS. Well, the IMAS software stack is tall and evolving. It can be fundamentally divided in three big layers. There is the access layer, the lower level, and the backend. The access layer depends on the language that you're looking at. So here I'm showing the access layer for Python, but again, there are multiple access layers depending on the language that you're using. Then there is the lower level, which is where all of the access layer coalesce, and they all use the same part of the code. And then the backend, which defines how the data is stored. As you can see here, as I try to convey here, things have been evolving, version 3, version 4, version 5. And so also the lower level has evolved in time. And so if you are a user up here trying to use this API, you may see things changing under your feet, which is, our experience has been that it's been hard to build on top of an infrastructure that is changing. And also this very tall software stack makes IMAS heavy, hard to install, and difficult to manage and keep up to date. So as we worked with IMAS, we started working with IMAS, we thought, can we adopt the benefits of the IMAS schema but avoid the disadvantages of a software that is, again, heavy, not smart, and evolving. And so we came up with, our solution has been this OMAS library. So OMAS is a Python library that it's been designed to really ease the interface of Python codes with IMAS. OMAS officially stands for Ordered Multidimensional Array Structure, but it's really a plain word between the OMFIT framework and the IMAS infrastructure. However, the OMAS library itself is independent of the OMFIT framework, and it can really be used independently on any by any Python software. This library started its development in 2017, and it's at this point is really mature. The services that OMAS provides are fundamentally to store data compatibly with the IMAS data model. And it offers convenient features that go beyond simple data storage. And it does all of that while not depending on the IMAS software. So if you want to try it yourself on your laptop, you can just go to the terminal and type pip install OMAS, and you will be able to start playing with the IMAS data schema right away. As I said, OMAS handles data accordingly to the IMAS schema, but does so independently of the IMAS software stack. And here in this cartoon, we see a OMAS user, and it can choose what format to save their data. So OMAS user have a plethora of formats to choose from, and in these, IMAS is just one of the supported formats. So this approach is great because for an OMAS user, OMAS users are isolated from any changes that happen to the IMAS API. As the IMAS API evolves, so does OMAS, but the user doesn't care about those changes. OMAS provides, as I said, convenient features beyond data storage, and here I just want to give an example just to guide you through what such features are. And so let's pretend, for example, that we want to translate some legacy equilibrium data to a format compatible with the IMAS schema. So here we read a legacy format like a GIQDisc file that most of you would be familiar with. This format contains, for example, a lot of data, but among which there is the safety factor of our discharge, as well as the information about the polyidal flux in a tokamak of the equilibrium. And so how do we do this? We instantiate an OMAS data structure object, so this ODS, and then we can start filling out the hierarchy of the equilibrium IDS. For simplicity here, we can create a shortcut. These hierarchies can be pretty lengthy. So here we create the shortcut to the equilibrium times less 0. And then we can fill out, for example, a scalar like the plasma current. We can fill out some 1D arrays like the polyidal flux and the Q profile, as well as some 2D array like as I said, the 2D polyidal flux information. As I said, OMAS enforces the IMAS schema with the graceful error handling. So let's say that, for example, someone mistyped IP and put it capitalized. And in this case, OMAS will throw an error, and it will also suggest what is the most likely thing that you meant to use. OMAS can use different syntaxes that make it very easy to construct paths programmatically. Here, for example, we're accessing the hierarchy kind of the same way you would do with Python dictionaries and lists. But you can also use a syntax just with a string, and where every path in the hierarchy is separated by a point. OMAS does automatic coordinate convention translation, which greatly simplifies mapping of legacy data. For people who are not familiar with it, one can define 16 possible combinations of the direction of the toroidal angle, poloidal angle, the sign of the graph psi and graph phi, and also the normalization of the poloidal field. And so in OMAS, all you need to do is to basically tell OMAS what is the convention that you're using when you're, for example, you're putting the data in. So in this case, we're telling OMAS we're using the convention number 1. The IMAS schema says that all of the data inside of IMAS, according to the IMAS convention, should use COCOS 11, and OMAS will take care for us to make the translation. So the data that we put in, it's now in COCOS 11. You can see that when we switch from COCOS 1 to COCOS 11, for example, psi has a 2 pi normalization difference. So here we were going from 0 to 1, and here we get to little above 6. In addition to handling COCOS, OMAS also does automatic grid interpolation, which enables really true centralized data communication that you would want if you're doing integrated modeling. So here, for example, we can define a grid that we want to use for psi, for example, going from 0 to 1, 11 points. And we can retrieve the data from OMAS, telling it not only what COCOS we want the data from to be in, but also what coordinate grid we want the data to come back. And so if we issue the same plot command that we have above here inside of this OMAS environment, we see that the result is different now. The Q profile is positive because in changing COCOS, and now both psi and the Q profile and all of the coordinates, all of the data that depend on psi, now would be returned to us on this grid that we specified. This is very important because if you're doing centralized data communication for integrated modeling, you always want your data to be coming back independently of who filled the data and how it was filled. Other features that are extremely helpful is, for example, the data slicing across arrays of structures. So, for example, we can take something that was a scalar, like the plasma current that we saw before, and request it as a function of time. So we get a time-dependent array. Same thing if you have something that is a 1D array, we can obtain a time-dependent evolution, for example, of the pressure. And this approach can also work for nested arrays of structures. So, for example, density is 1D, ions, we can have multiple ions as a function of time. So this will return us a 3D array. OMAS can cast its data as X-arrays, complete with the units and coordinates. This is very handy if you're used to use X-arrays as part of your coding. And it can seamlessly handle uncertain data with uncertainties package in Python and units with the pint package in Python. And also, OMAS can do automatic translation of code parameters from and to the XML representation as required by the IMAS standard. So in IMAS, if you're running a code, you can store the parameters that you use to run the code under code parameters. And here in OMAS, you can just use the standard OMAS syntax to set up and read these code parameters. But when you work with the IMAS infrastructure, that gets automatically translated to XML as the IMAS standard requires. OMAS also comes with a rich set of libraries for physics and plotting. Here I'm highlighting just a few. For example, you can make IDSs self-consistent internally. You can map between complex triangular grids to rectangular grids. You can evaluate fields in different ODSs based on the data that is in other IDSs. For plotting, We have plotting for different, all kinds of IDSs. This is an example plotting all of the diagnostics, line of sights, and measuring locations for D3D, all this done through OMAS. And on the right, you can see some of these time-dependent plots, for example, for the equilibrium and the trajectory of the ECH beams as modeled by ray tracing. And with the time slider above that one can scroll to see things evolve in time. OMAS also prototyped tensor representation of the IMAS data to improve the I/O performance of large data sets. This is something that it's been implemented in the HDF5 backend in IMAS, or at least that will be implemented this way in the HDF5 backend. And to make a long story short, if you have big arrays of structures, the time to read and write the data to file kind of scales linearly with the number of elements in your data array, in your arrays of structures. And instead, if you map the same data to kind of a tensor representation where you have kind of squashed these arrays of structures and added just one dimension to your data sets, you can then read and write this data in bulk, and now the time to write this data effectively doesn't depend on the size of that dimension. And in OMAS, this is done quite elegantly with this ODX data format that can translate between the ODS hierarchical representation and this tensorized representation. Now let's see OMAS in action. This is inside of the OMFIT framework. If you want to hear more about OMFIT, I invite you to join the talk by Sterling Smith tomorrow morning as part of this mini conference. So OMAS has been used inside of OMFIT to enable centralized data exchange. OMFIT has interfaced with over 100 Fusion formats for a long time and has been used this capability to do point-to-point data communication. Now OMFIT is using OMAS as the hub to translate between these legacy formats and IMAS. And this has really, as I said, enabled new workflows that use centralized data communication. So this is where we've been with OMFIT for a long time. This is where we would like to be, but until all of our components and physics codes that that we don't develop but other people develop, until these don't read and write data directly from IMAS, really the situation is something more like this. So where we need to define some kind of adaptive layer that translate the legacy formats to the IMAS format. And because OMFIT can, as I said, read and write many Fusion data formats, the combination of OMFIT and OMAS are really the perfect universal translators in Fusion. So the way we've done this is that we have instrumented the OMFIT classes with two methods, a to OMAS method and a from OMAS method that can be used to effectively translate between legacy format and the IMAS format. Here is an example of this in action where we read the legacy format, again this EFIT GIACUDISC file format. We convert it to an ODS using the to-OMAS method. We can use OMAS to save this data, for example, to the IMAS infrastructure. That's how you do it, in case you were wondering. So we can say ODS save to IMAS, machine pulse new, and the data gets put into IMAS. We can read this data back. And once we have this data into a new ODS, we can generate the legacy format again by instantiating an empty GIACUDISC class and filling it from the ODS that we just retrieved from IMAS. Once we have this object, we can deploy it to file and we get our file back. These OMFIT classes I really want to highlight can be used outside of the OMFIT framework. There's been a lot of effort recently to decouple these classes from the framework itself. So if you want to install those, you can just go on PyPy and search for onfit, and then install the class that is most useful for you, just with the pip install onfit, and then name of the class. The module inside of onfit that best exemplifies the use of OMAS is the step module, which is a module that is designed to perform self-consistent theory-based predictions of tokamak plasmas. In step, the physics codes are wrapped into steps that exchange data via OMAS. Here you can see the codes that we're using kind of grouped by physics topic. And this approach, because we are using the centralized data structure of OMAS, this makes it device agnostic, and adding new code is simple. The effort really scales just with the number of codes, not squared. And the data flow and the workflow in step are decoupled to one another, meaning that we can execute codes in arbitrary order, which allows us to execute a variety of workflows, for example, open loop prediction, feedback control, and optimization studies as well. This is a team effort. This is which is growing very rapidly. And I want to highlight two talks at this APS conference, one by Brandon Lyon and Tim Slenderbrook, that talk more about step. Here is some results from Tim showing a comparison of step predictions for confinement time compared with the experiment for a large subset of cases in the ITER Y92 scaling. So in conclusion, OMAS is a convenient Python library for working with the IMAS data schema. It can handle IMAS compatible data with different storage technologies. It's trivial to install. It does not require a working IMAS installation for you to use it. It can interface with the IMAS software if it's available, if you want it. It's easy to use, and its capabilities go well beyond simple data storage. onfit has embraced OMAS, and it has really enabled the integration of onfit with existing IMAS modeling efforts. And if you're interested, again, it's very easy to install, and you can try it out for your own Python software. Thank you.